All right, what we want to talk about now is the idea of torque. So to look at torque, to understand what torque is and how it kind of works, what we need to do is we actually need to take a step back and look at Newton's second law, that the sum of the forces on an object divided by its mass equal is the acceleration. So the acceleration an object experiences is the sum of the forces divided by the mass. Now it turns out that there's also an equivalency for rotation, and alpha is the sum of the torques divided by I, where alpha is your angular or rotational acceleration. This is the rotational acceleration. This, of course, was the moment of inertia. And this new letter tau is the torque. So just as forces are responsible for changes in motion, in linear motions, we basically take our forces and divide it by mass to get the acceleration. Here we have some torques. We sum up torques and we divide by the moment of inertia, which is like a rotational mass, this is mass was inertia, this is rotational inertia. So we sum up our torques, divide by I, and that tells us our alpha, our rotational acceleration. So this is how fast the object, this is how quickly you're gaining omega. So there's a relation between torques alpha and how big omega gets, just like there was between forces, accelerations, and your velocity. So the idea is that torques then are going to be responsible for rotation. So torque causes rotation. And what we want to look at is we want to look at how torques cause rotation and what's involved with them. But we needed to understand the comparison between the two to start thinking about torques. So what is torque? The simple way to think about torque, we can think about this in two examples. So let's say we have a door, and the door is attached to the wall here by a hinge. So this is your door, and here's the hinge. Now, if you've ever gone up to a door, and when you push on a door, if this is, the hinges are the rotation point, rotation axis, is along the wall where the door and the hinges meet. Now, when you push, if you push here, it's very hard to open the door, because when you're pushing here, your hand is very close to the hinges and it's hard to open. Versus when you push out here, what happened? Well, if we said that torques are responsible, we said that torque is responsible for the rotation. And torque, it turns out, is equal to the what we call the lever arm times the force. So why is it that it's easier to open the door when you push near the opposite end of the hinge versus near the hinge? Well, the force of your push is the same. What changed is this thing called the lever arm. And the lever arm is simply the distance. The lever arm is the distance between of where the force is applied from the rotation axis. So the farther you go from the rotation axis, the larger your lever arm, so you get more torque for the same amount of force. Now, that's just the idea of opening a door. Another example that a lot of people, some people, not everybody, relates to is the following. Let's say you have some bolt. You have some bolt that you want to try to, you have some bolt, a hexagonal bolt, and you want to try and free up that bolt, and it's being very stubborn. So normally you push with some force that you can apply. And if that bolt doesn't turn because it's rusted or a little stubborn, what most people will do is they will attach what's called a breaker bar on top of the wrench handle or a pipe. And so what did you do? This is your old lever arm. Now when you apply your same force, you apply the same force here, what got bigger? Your lever arm got larger, so for the same force times the bigger lever arm, you generate more torque, and you might be able to start getting that bolt to rotate. Now, of course, you probably should spray in some of WD-40 too, just in case it's rusted. You don't want to pop the head of the bolt off, then you've got to like tap it and stuff. But in general, the lever arm will give you, extending the lever arm gives you more torque for the same given force. You didn't change your strength, you changed the lever arm to generate the torque to get the bolt to move. So this is kind of the idea of torque. This net torque then, when your lever arm times your lever arm times your force goes into that equation, your second law for rotation, that alpha equals the sum of the torques divided by I. And because you have some net torque, your torque got bigger for some I and whatever, minus those frictional forces and all these other things going on, and you were able to get an alpha. And so this is kind of the idea. We have this this idea of torques being lever arms times force. And lever arm is the distance of where the force is applied to the rotation axis, which would be like the center of the bolt. So let's take a look at another example of torques and rotations. So we said that alpha is equal to the sum of the torques over I. So just like we had equilibrium on an object when we summed up our forces, we can have rotational equilibrium. And that's when you sum up your torques, when the sum of the torques equals 0. That's rotational equilibrium. And so an example of this that's kind of classic is the teeter-totter. So when you're thinking of the teeter-totter, what happens? You have a rotation point, which is the center of the teeter-totter. And usually you have, like 2 kids or whatever sitting on the teeter-totter. And you can call, let's say this kid is some, 1 meter away or 2 meters away. And this kid over here, let's say we want to figure out how far away that kid needs to be to maintain rotational equilibrium. Now let's just assume that this kid, he weighs 50 kilograms, and this kid over here weighs 100 kilograms. So what we can do is we can use our rotational equilibrium. Now we have to think about something because we said that torques cause rotations. So what we're saying is there's some rotation about that where the teeter-totter sits. This kid's force is down from gravity. This kid's force is also down from gravity. So this force wants to cause a rotation this way. This one wants to cause a rotation the other way. This is what we call a counterclockwise rotation, and this is what we call a clockwise. Now normally the counterclockwise you'll call positive, and clockwise is negative. And so when you sum up your torques, a counterclockwise is positive and a clockwise is negative. So let's take a look at how we would do this. We'll call this side, we'll call the counterclockwise torque 1. And so when we're looking at summing our torques, we have torque 1 minus torque 2, because torque 2 wants to go this way, torque 1 wants to go that way. So what do we get? We get, I'll have to erase this. We'll get torque 1 and torque 2. We get the sum of the torques is torque 1 minus torque 2. We know that has to be 0 if they're in equilibrium. So what do? That means we can add torque 2 over here. Torque 1 has to equal torque 2. Well, what's torque 1? Well, it's this distance, 2 meters, times the force, which is mass times gravity, 50 times 10. That has to equal some unknown distance that we're looking for times the mass of the kid, well, that's an adult, times gravity. So when we solve for x, we divide this side by 1,000, and x is then 50 times 10 times 2 divided by 1,000. This is 500. 1,000 divided by 1,000. This kid only has to sit 1 meter away to keep the teeter-totter in balance. If that kid sits in too close, then there's a net torque, and this kid goes down. If he sits further out than 1 meter, then his side has the net torque, and the teeter-totter rotates the other way. But this is the idea of looking at torque for rotational equilibrium. And of course, you could also look at this problem and say, oh, the kid's already a given distance, how heavy must he be, and things like that. You can juggle these problems around differently. But the idea of rotational equilibrium is that the sum of your torques is equal to 0.